Hello, this is Matt Dean with A Plus College Ready, and today we're going to look at some uniform circular motion practice problems. So practice problem 1 says, what is the maximum speed at which a car can safely travel around a curve if the radius of the curve is 100 meters and the coefficient of friction between the tires and the road is 0.2? Well, in this case, what you've got to know is that the frictional force is actually acting toward the center of the circle. So if we drew a free body diagram for this car, we would have weight acting down. Assuming we're on flat ground, we have a normal force acting straight up. Those two cancel out. The frictional force is acting toward the curve. So that frictional force is a net force. It's also a centripetal force. So to work this problem, we're going to set the frictional force equal to the centripetal force. We know that the frictional force is equal to the coefficient of friction, mu, times the normal force. And we know that the centripetal force is equal to m v squared times r. mv squared over r, rather. So since we're on flat ground, we also can assume that the normal force is equal to the weight. So let's make a substitution. We'll substitute mg for normal force for weight, set that equal to mv squared over r. You can see that the masses cancel out. And in this case, we're trying to solve for velocity. So if we solve this out for velocity, we end up with v equals the square root of r times mu times g. And if we substitute in our numbers here, we end up with r is the radius of curvature, so that's 100. Mu is 0.2, and we'll use a g of 10. We end up with a velocity, once we take the square root of that whole quantity, of about 14.1 meters per second. All right, so here's practice problem 2. If the distance between two objects is increased by a factor of 8, while the mass of each object is increased by a factor of 4, how is the force of gravity between the two objects affected? Give a numerical answer. Well, first of all, we need to think about Newton's law of universal gravitation. And this is what it looks like. G is the gravitation constant, so that's always the same. If we say this is the original force, what we're doing in the new problem is G doesn't change. We're increasing M1 by a factor of 4. We're increasing M2 by a factor of 4. We're increasing the distance between the two objects by a factor of 8. Well, that has to be squared, so we've got to have 8 squared here on the bottom. So that becomes 64. So you can see that we've got 4 times 4 on top, 16. We've got 64 on the bottom. That reduces down to 1/4. So what that tells me is that the new force, after doing the increases in mass and distance, the new gravitational force is 1/4 of the original force. All right, so here's number 3. A satellite of mass 5.5 times 10 to the 5th kilograms orbits the Earth. We're given the mass of the Earth at an orbital distance of 6 times 10 to the 6 meters. If the satellite must maintain a constant distance from the Earth, what is the satellite's orbital velocity in terms of meters per second? And also, what's the period? So what we've got to remember here is that it's the centripetal force that's keeping the satellite in orbit. And that centripetal force is the gravitational force between the satellite and the Earth. So we're going to say centripetal force is equal to gravitational force. Remember that centripetal force is mv squared over r. And that's equal to the gravitational force, which is g, m. In this case, this m over here on the left, this is the mass of the satellite. So I'm going to say mass of the satellite times the mass of the Earth over r squared. So what you can see is that this right here is the mass of the satellite. Those are going to cancel out. So if we continue to solve this for v, we'll multiply both sides by r. This r is going to cancel with one of those. We're going to take the square root of both sides. And that's what we get when we solve it out. So we're going to substitute in G, 6.67 times 10 to the negative 11th. We're going to substitute in the mass of the Earth, 5.97 times 10 to the 24th kilograms. And we're going to substitute in the orbital distance, 6 times 10 to the 6 meters. We'll take the square root of that whole quantity and end up with a velocity of 8.15 times 10 to the third. And that's in meters per second. So that satellite is moving really, really fast. So next we want to find the period. And what we know about the period, an equation that will help us with this is that the velocity of something going in circular motion is equal to 2 pi r over the period. So if we solve that for the period is going to equal 2 pi r over v. Well, in this case, r is that orbital distance. So we're going to end up with 2 pi times 6 times 10 to the 6th meters. And all that's going to be divided by this velocity right here, 8.15 times 10 to the third meters per second. And when we do the math, we end up with a period of 4.62 times 10 to the third seconds. And remember, that's the time it takes for one complete orbit. All right, here's practice problem 4. A planet has 3 times the mass of Earth and 5 times Earth's radius. The magnitude of the gravitational field near the planet's surface is. What we want to realize here is that the weight of an object is caused by the force of gravity. Remember that weight is mg, and it's the mass of the object. In this case, I'm going to put mass of object times g. And the force of gravity is the gravitational constant times the mass of the object times the mass of the Earth all over r squared. So what you can see is the mass of the object here is going to cancel out. And that the g, in this case, this is the strength of the gravitational field, is equal to the universal gravitation constant times the mass of the Earth over r squared. Now in this case, we don't need to plug in g or me because we're looking for this in terms of comparison to Earth. All we really need to look at is this r. And what we can see is if we plug the radius in this new planet is 5 times Earth's radius, so we square that. And so they're going to have 25 here on the bottom, 5 squared. The mass of the new planet is 3 times that of Earth. So this is going to be 3 times me. So essentially that's telling us is that the new planet its gravitational field is going to be 3/25 of Earth's. Remember that Earth is 10. So it's going to be 30 over 25, which is going to reduce down to 6/5, and that's measured in newtons per kilogram. So again, the strength of Earth's gravitational field is newtons, 10 newtons per kilogram. So our answer here is B, 6/5 newtons per kilogram. All right, here's practice problem 5. 2 pieces of space junk of equal masses are in circular orbits around the Earth. Object A has a speed of v. The orbital radius of object B is 16 times that of object A. What is the speed of object B? Well, what we've got to remember to work this problem out is an equation we derived in problem 2 or 3 earlier. Remember, it's the force of gravity that's acting like a centripetal force. It keeps objects in orbit. Remember that the force of gravity is g times the mass of the object times the mass of the planet, we'll say in this case. In this case, it's the mass of Earth over r squared. Centripetal force is the mass of the object times its velocity squared over r. So what we can see, again, mass of object cancels. If we solve this out for, in this case, v, multiply both sides by r. That cancels one of these here on the bottom. So we end up with v equals the square root of g me over r. So we're seeing that the orbital radius of B is 16 times that of A. What that's going to tell us is that the speed is going to end up being about the square root of 1 over 16, because it's going to be 16 right here. So the square root of the radius, the speed of object B is going to be equal to the square root of 1 over 16 of the speed of object A. So that's going to end up being V equals 1/4 of the speed of object A. Which means in this case, our answer is D. All right, so here's practice problem 6. A satellite orbits a planet in circular orbit. The mass of the satellite and the distance between the center of the satellite and the center of the planet are known. What additional information is needed to calculate the speed of the satellite? So just like we saw in practice problem 5, we derived this equation for the speed of a satellite, in this case going around Earth. And the problem tells us that we know the mass of the satellite. We really don't need to know that. We know the distance between the center of the satellite and the center of the planet. That's what R is. We know the universal gravitation constant. So the only other thing that we need to know to find the velocity of that satellite is the mass of Earth, or the mass of the planet. In this case, we're assuming it's Earth. So our answer is going to be C. All right, so here's practice problem 7. So a person who weighs 1,250 newtons on Earth travels to another planet that has 3 times the mass of Earth and 4 times the radius of Earth. What's the person's weight on the other planet? Well, what we've got to realize is that the weight is caused by the force of gravity. So the weight is going to change, but the weight is made up of mg. The force of gravity is a universal gravitation constant. In this case, times the mass of, we'll say, the person, times the mass of the planet over r squared. So in this case, we're going to assume that the mass of the person doesn't change. Big G doesn't change. But what does change is the mass of the planet. The mass of the planet is 3 times that of the mass of Earth, and the radius is 4 times that of Earth. So this becomes 4, and that 4 gets squared. So that's telling you that the new mass is going to be 3 on top over 16 on the bottom. 3/16 of the original weight. And if we take 3/16 of 1,250, we end up with about 234 newtons as the weight of the person on the new planet. All right, so here's practice problem 8. So we've got a ball that's being whirled in a horizontal circle. The ball undergoes uniform circular motion. Which of the following best illustrates the direction of the velocity when it reaches point X? Well, here's point X down here. So the ball's going around the circle like this. So it gets to point X, still going in this direction. What you've got to know is that in uniform circular motion, the velocity of the object is always perpendicular to the radius, to the direction the force is coming from. So the force is coming from here, from this string. The force is pointing always toward the center. The velocity is going to act perpendicular to that force at that instant in time. So our answer here is going to be C. All right, so practice problem 9 is a continuation of problem 8. In this case, we want to know what's the direction of the net force acting on the ball at point X. Again, the ball's moving this way, counterclockwise. When it gets to this point, what's the net force? What you've got to remember is that in uniform circular motion, the net force is the centripetal force. And the centripetal force is always acting toward the center of the circle. So our answer here is going to be A. All right, practice problem 10 is also a continuation of 8 and 9. In this case, we want to know what's the direction of the acceleration of the ball at point X. So again, the ball's going in a counterclockwise motion. When it gets here at point X, remember the net force is the centripetal force. It's pointing toward the center of the circle. Anytime an object is moving in uniform circular motion, it's always going to be accelerating toward the center of the circle, toward the direction of the centripetal force, which is the net force. So in this case, A is our answer. All right, here's our last practice problem. Practice problem 11. Two bags contain an equal number of identical masses. The two bags are separated by a distance of r. 1/3 of the masses from one bag are moved into the other bag. If the magnitude of the original gravitational force between the two bags was F, what is the magnitude of the gravitational force after the masses are transferred? So when we started off, the gravitational force was something like this. But what we do now, let's say we took 1/3 of the masses from M1 and we moved them over to M2. What that means is that the mass of M1 now is going to be 2/3 of what it originally was. And the mass of M2 gained an extra third. So it's now 4/3 of what it originally was. R didn't change. So all that changed was the distribution of the masses. So if we multiply those fractions on top, we end up with 8/9. And what that means is that the new force is, the new gravitational force between the two objects is 8/9 of what the original gravitational force between the two objects was. That means that answer D is our answer here. All right, let's get started with practice problem number 12. So the figures show a cart moving at the bottom of a dip. We see that here. Moving over the top of a hill. See that here. And moving at the top of a vertical loop, like that. In each case, the normal force acting on the car is Fn and the weight is Fg. In which case is it always true that Fn is greater than Fg? You're going to see the same kind of question 2 or 3 times during the rest of this presentation. When you have circular motion, which this is, even though we don't see a whole circle, we could still think of it as if it was circular motion. This cart has got to accelerate up the circle. The force that's causing it to go up the circle in this case is the normal force. It can only accelerate up that circle if that normal force is greater than the gravitational force, which is acting down. So A is our answer. To accelerate up a circle like that, the normal force has to be bigger than the gravitational force. So our answer is A. Here we see the same question essentially, but this time we want to know, when is it true that Fn has to be greater or less than Fg? And this one I hope is pretty obvious. Answer here is C. And that's because remember that the normal force is essentially almost like a reaction force. So when something pushes down, the ground pushes back, the surface pushes back. In this case, there's not a lot of push going on between the cart and the incline. If it wasn't going very fast, it would actually fall. In this case, it's going fast enough so that it's still touching. There's still some push against that incline or the surface, but not much. Point being, in this case, the gravitational force is much bigger than the normal force. That gravitational force is causing the cart to accelerate down that circle because it's larger than the normal force. All right, so here's another one. This is question number 14. 3 moons with masses indicated above. So mass 3m, mass m, and mass m are initially far away from each other. The gravitational potential energy of the 3 moon system is 0. The moons are then brought together, so they're moved close together, a distance of r. Notice they're all a distance of r from each other. What is the gravitational potential energy of the 3 moon system once the moons reach a distance of r? Well, you got to remember that the gravitational potential energy equation is this. It's negative g m over r. And those are our 2 masses. So what we're going to have to do in this case is calculate the gravitational potential energy for each pair of moons and then add them all together. So let's start with this one and this one. So that would be G 3m times m over r. Now let's do the same thing for, again, this top one and this one over here. And notice it's going to be the same. Don't forget the negative sign. as the other one. So negative g 3m m over r. And then finally, let's calculate it for the two bottom ones. So that's going to be negative g m over r. Now we can combine those m's. We can multiply them together and get m squared in each of the terms, and then add them up. And when we do that, we end up with negative g 7m squared over r. And all we did is just square the m's, in this case, multiply the m's times each other, and then add up all the coefficients. That's our gravitational potential energy of this 3-moon system. So looks like answer C is our correct answer. All right, on this one, 2 satellites, each orbiting the Earth. Satellite 1 has a speed of v. Satellite 2 has an orbital radius 4 times that of satellite 1. What is the speed of satellite 2? So here's the way you're going to have to approach this one. Think of it this way. The force of gravity is what causes the centripetal force that makes these satellites orbit the Earth. So let's set those two equal to each other. We know that gravity is big G times the mass of, in this case, of the Earth, mass of the satellite, over r squared. And that's going to be equal to the centripetal force, which is mass of the satellite, v squared, over the radius. So let's solve this out for r, or for v rather. Let's solve for the speed. So let's multiply both sides by r. Cancels over here. One of these cancel out. And then let's divide both sides by the mass of the satellite. So that's going to cancel over here. It's also going to cancel over here. And then let's take the square root of both sides to get v equals g me over r, the square root of that whole quantity. Now here's what we got to think about. The mass of the Earth is constant. G is the universal gravitation constant. The thing that changes here is the radius. And for satellite 2 rather, it's 4 times what it is for satellite 1. So let's plug in a 4r right here and see that when we take the square root of 4r being on the bottom, we take the square root, we're going to end up with a speed for satellite 2 that's essentially 1/2 of what it was for satellite 1. And that choice is D. And it's 1/2 and not 2 because this 4 is on the bottom of a fraction. So when we take the square root of 1/4, which is essentially what we have there, we end up with the square root, we end up with 1/2 of the original velocity. All right, it's number 16. A small box with no friction slides across a track toward a circular loop. The block has more than enough speed to remain firmly in contact with the track as it goes around the loop. Which of the following choices describe the magnitude of the block's acceleration at the top of the loop? So think about this dot as the block. We know that when it's at the top, there's a force of gravity acting down on it. That's the weight. But also when it's at the top, the normal force is actually pushing down on it. So we end up having 2 forces acting toward the center of that circle. This is the weight. So by itself, it should cause the thing to accelerate at g, but there's another force, the normal force, acting in that same direction, which means there's a bigger net force than the weight. Therefore, there's going to be a greater acceleration than the acceleration due to gravity. So that is answer A. Now, number 17 is very much like the first problem we did today, I think number 13. So a cart of mass m rolls past the circular bottom of a hill, point Z. Which of the following statements about the normal force exerted on the cart at point Z is correct? So think of this as if it's a circular motion kind of problem. When the cart gets down here, it's got to accelerate up that circle. If there's no other external forces besides the normal force and the weight, the normal force has to be greater to cause that thing to accelerate up that hill. So at point Z, the normal force is greater than the weight mg. And that is choice B. Again, that's at least the second time we've seen that in this problem set. So probably going to see a question like that on the AP exam. It's easy. Just know at the bottom of a loop that the normal force is going to be greater than mg. And at the top of the loop, mg is greater than the normal force. So here, our rover lands on the moon Titan and explores its surface. The average gravitational field on the surface of Titan is 0.138. The weight of the rover is defined as the gravitational force exerted on it. Which of the following statements are true about the rover's weight? All right, so the rover's weight was constant until it reached the surface of Titan. That's A. Remember that gravitational force is G, mass of the, we'll say mass of the planet in this case. We'll say mass of the, what are we talking about? The rover over r squared, where r is the distance between the centers of the two objects. So as this rover approaches Titan, the r between them is going down. And since r is on the bottom of that fraction, as r goes down, the gravitational force is going up, which means the weight is going up. So this is not constant. It's wrong. B, the rover weighs less on the surface of Titan than on the surface of Earth. Well, here's the gravitational field strength of Titan. But I hope you remember that on Earth, that gravitational field strength is 10 newtons per kilogram, much more than it is on Titan. That means the force of gravity on Earth is way more than it is on Titan. And therefore, objects do weigh a lot less on Titan than they do on Earth. So this is a correct answer. C, the rover's weight always equals the normal force exerted by Titan on the vehicle while it is landing. You know, there's a lot of things going on. Is it landing flat? Is it landing at an angle? There's all kinds of weird things going on there. This does not necessarily have to be true. But notice that D does. The rover's weight increased while it was descending, because again, as R goes down, FG goes up. So our answers on this one, B and D, look good. All right, so this one is very much like those curved hill problems that we were talking about a second ago. So a boy swings a ball on a light rod at a constant speed in a vertical circle, as shown above. Which of the following correctly describe the force exerted by the rod on the ball when the ball is at locations A and B? When the ball is up here, gravity can help it accelerate downward. But when it's down here at the bottom, when it's at B, the force exerted by that rod has to be greater than the gravitational force to make that thing accelerate up. So point being, the force from the rod at B has to be greater than anywhere else because we're going completely against gravity, accelerating that thing up. So our answer is A. And that's the third example where we've seen a very similar question. The other two were asking about normal force, but it's still the same kind of thing. It's you're accelerating something up from the bottom of a circle. All right, this one. A satellite is in a circular orbit 800 kilometers above the surface of a distant planet. The planet has the same mass as Earth, but a radius that is 80% of Earth's. The acceleration of the satellite due to gravitational force exerted by the planet is most nearly. So again, think of the force of gravity equation. So we'll say the mass of the planet, we'll call that MP, the mass of the satellite over r squared. So regardless of which planet we're talking about, G is the same. The mass of the planet is the same. The mass of the satellite is the same. What's different is the radius of the planet. That's not what r is. R in this equation is the distance between the centers of the two objects we're comparing. So as long as the satellites are the same distance from the centers and the masses are the same, the gravitational fields, the acceleration due to gravity, going to be the same, which means our answer here, C. We know that gravitational field always acts toward the center of the planet. So 10 meters per second squared toward the center. And they're trying to confuse you by talking about the radius, Remember, r in this equation is the distance between the centers of the objects, not necessarily just the radius of the planet. All right, here's another one. On another planet, not Earth, a ball is in free fall after being released from a rest height at time 0. So the ball is falling. A graph of the height of the ball above the planet's surface as a function of time is shown. What is the acceleration due to gravity on the planet? So notice this thing starts with an initial position. We'll call that x sub 0 of 100. And then over here, this is at time 4 seconds. It's fallen, and some of these marks may be hard for you to read on this video, but let's see, this would be each one of these little faint lines is worth about, looks like 4. So 44, 48, 52. So our final position, 52 meters. So let's calculate a displacement. We know that's final position minus initial position. So our displacement is negative 48 meters. That's how far we fell. Now that you might not think that can help, but what you're going to do is you're going to go to this kinematic equation. We're starting from rest, which means the initial velocity is 0. So that term doesn't matter. So we're left with this. Let's solve that out for acceleration, which in this case will be the acceleration due to gravity on that planet. So multiply both sides by 2. That'll cancel this out. Divide both sides by t squared. That'll cancel this out. So we end up with acceleration equal to 2 delta x over t squared. So in this case, that's going to be 2 times negative 48 meters divided by 4 seconds squared. And once we do the math on that, we end up, we're going to come up with negative 6 meters per second squared. This question probably really should have asked for the magnitude of the acceleration due to gravity, but they're looking here for answer D. All right, so here's our last question for this problem set. So a block is attached to the end of a string and initially moves at a constant speed in a horizontal circle of constant radius. The radius is then decreased slowly while the speed remains the same. Which of the following graphs best represents the force exerted on the block by the string as a function of the radius? Well, think of our equation for centripetal force. Here's what we know. We know that the mass of the object, that's going to be the same, not changing in this problem. We're holding the speed constant. But what we're doing here is we're decreasing the radius. And since that r is on the bottom of the fraction, as r goes down, the centripetal force, the force in the string in this case, has to go up. So as r goes down, FC goes up. So we need to figure out which one of these graphs would show that. And I'm hoping that you see that this graph shows that, and so does this one. The other two show the opposite thing, that as r goes down, force goes down. Or as r goes up, force goes up. We got to figure out which one of these is correct, A or D. And because of this square term, we're not going to have a straight line. We're going to have a curve. So A looks like the best answer here on problem 22. All right, that's it for our uniform circular motion and gravitation problems. Hope that helps.